be the right topic to talk here. So I will be showing some of the Newton scattering results on these low-dimensional magnetic systems. And the title, as you see, the physics of novel magnetic states in reduced dimensions. So as you know, the magnetic systems, the dimensionality-wise, we are more familiar with the 3D magnetic materials. And when we talk about the 3D magnetic systems, basically the exchange interaction, magnetic exchange interaction, whether in terms of crystalline material, whether it is along crystallographic A, B, or C, all three are there, and you cannot neglect any one of those. So, but in case of 2D magnets, you know, the exchange interaction, let us say the planar exchange interaction, AC plane, if it is much stronger compared to the outer plane, that is B direction, then this can be treated as a 2D magnets. And for 1D magnets, suppose the exchange interaction along the length, that is along the chain, that is C direction, much stronger than both A and B. That means A and B can be neglected along this plane. In that case, we can treat this as 1D magnets or quasi-1D magnets. Of course, the Hamiltonian, as you see the terms, whether the G component, X component, Y component, whether depending on the relative contribution from all these three exchange interactions, it will decide what kind of magnetic materials it is. So we know there is a famous theorem, the Marmin-Wagner theorem, which tells us whether the presence or absence of long-range magnetic ordering at finite temperature, and it was for isotopic Heisenberg spins. And we know that for Heisenberg spins, the theorem says that there could be long-range magnetic ordering only when the space dimensionality is 3. So if space dimensionality is 2 or 1, and if you are dealing with Heisenberg spins with short-range exchange interaction, there cannot be any long-range magnetic ordering. Similarly, for Ising spins, we can have ordering for d equal to 2 or d equal to 3. For xy, obviously for d equal to 3 we can have. But of course, there are exceptions, as you know, that depend upon what kind of, see here it is isotopic exchange interactions with the Heisenberg spins, but if there are anisotropies or even let us say dipolar exchange interaction, in that kind of scenario, even there could be magnetic ordering. Of course, this theorem was later on extended by Bruno, where it was shown that even for long-range RKKY exchange interaction, this theorem holds good. See, for 1D systems, for example, when the spins are forming this kind of chain, and you have uniform chain, and the exchange interaction between all different atoms are same, that is J1, 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 so that is called uniform chain. And if you have a dimer system, let us say these two spins where you have J1, and here the two different exchange interaction, that is J2, so your unit is this one. So it is the dimer. Similarly, for trimer spin chain system where J1, J1 and J2, and for tetramer it is J1, J1, J1 and J2. So for example, when you go to dimer system from the uniform chain, and in this case of alpha, which is nothing but the ratio of this J2 by J1, that is this is our J2 by J1, that ratio depends, if it is alpha to alpha 1, you see the magnetic susceptibility as a function of temperature, you do see the magnetic response variation. So that means it matters what is the ratio of this J2 with respect to the G1. So that dictates the magnetic properties. In case of 2D systems, there are different kinds of geometries, how the spins are arranged. One can have square lattice, where the spins are at the corner of a square lattice, or even honeycomb lattice. In this case, there are 4 nearest neighbor of each spin. Here, in this case, 3, or in case of Kagome, there are 4 nearest neighbor. And for triangular lattice, there are 6 nearest neighbors. So in this case, in these two cases, A and B, that is square lattice and honeycomb, there is no frustration if we are dealing with only the nearest neighbor exchange interactions. Whereas for Kagome and triangular lattices, even the nearest neighbor exchange interaction causes the frustration, and you know the famous this case for the triangular lattice with the, of course, with the Ising spin, or you deal with the x, y, or Heisenberg spin. So this kind of 2D lattice, they are prone to give different kinds of novel magnetic states, non-collinear magnetic ordering, spin liquid state, even degenerate, they are all, they show the degenerate magnetic ground states. So in my example, I will be giving some of these such cases, and one such example I show from this study where we are dealing with the copper spin half, this blue one. See, the copper forms the plane, and these are the bromine. So this copper located in a square lattice here. So you have J1, and this is J2, and there could be J3, and so this is the square lattice case considering the spin half of copper. And of course, this kind of crystal structure we get, as you know, from powerful neutron diffraction experiment, where these lighter atoms can be seen in presence of heavier atoms, and so on. And also, I'd like to point out that if you look at the crystal structure, see the copper plane, and between two copper planes we have non-magnetic NbO6, niobium O6, and the strontium. And you look at the c-axis length. So this is very much separated, and the magnetic exchange between these two planes, they hardly propagate. So it is a basically 2D system, or you can say quasi 2D system. So the crystal structure puts the ingredient, in this case, ingredient for the 2D magnetic system. And over and above, it is a square lattice, and also we deal with copper spin half. So it is a very good quantum system with the square lattice spin arrangement. Now, by doing powerful neutron diffraction experiment, this is the magnetic structure we get in the plane. In plane, we get the commensurate independent spiral order of the copper spin half, and this is the where the propagation vector that gives the size of the magnetic unit cell with respect to the chemical one, with respect to the nuclear one, and you see the propagation vector. What I have plotted here in this 4a by 8b by 3c, the cell size over that the magnetic structure is shown, and experimentally what we get in this case, copper is of course in 2+, but order moment what we find the 0.79 Bohr magneton at 2 Kelvin, and of course that means there is a, what is expected if the full moment is there, as you know, 1 Bohr magneton. So there is a quantum fluctuation, and theoretical calculation, as you know, that for 2D system dealing with spin half antiferromagnetic square lattice, it is expected to be 0.6. So it is quite reduced compared to 1, but of course slightly higher than the 0.6. So it tells us definitely there is quantum fluctuation is involved in this case, and which gives this kind of beautiful spiral magnetic ordering. And when we extended this study under magnetic field, that was under zero magnetic field, that was the ground state. Okay? Under external magnetic field, when we plot this, the ordered copper moment in Bohr magnetic unit, see, we get 3 phases. This is the ground state, which I just showed you the spiral structure, that is the antiferromagnetic 1 spiral structure. But above this magnetic field, it goes to second magnetic phase, that is antiferromagnetic 2. What is the difference between this antiferromagnetic phase 2 is that this k vector, the magnetic propagation vector, changes from this to this. So, and over and above, we do get another phase, that is the ferromagnetic phase. So it is the coexistence of this antiferromagnetic 1 goes to antiferromagnetic 2, and also the ferromagnetic phase. So this kind of beautiful phase diagram we could draw by doing experiments under magnetic field. Now, when we map this, our experimental observation, with the available theoretical phase diagram, where you see the phase diagram J2 by J1, this is the second nearest neighbor with respect to the first nearest neighbor exchange constant, and this is the third nearest neighbor, that is the J3 with respect to the first nearest neighbor exchange constant. In this J1, J2, J3 model, the phase diagram, the spiral ordering lies here. That means when the J3 by J1 is higher than 0.25. So it only tells that in this system, the J3 is indeed very important, and that's why we are able to get this spiral ordering. But of course, these exchange constant can be measured, as you know, by doing inelastic neutron scattering experiment, but we need single crystal, and we are working in that direction. Now, I give another example, again the 2D square lattice. So, these are all naturally grown magnetic systems, spin systems. So, this is here is the crystal structure. Again, we get by doing this kind of neutron diffraction experiment, and we draw the crystal structure where we are dealing with VO5 square pyramidal. And here the vanadium is in 4+ state, and this is the 3D1 electronic configuration, and that is responsible for the magnetism in this case. And VO5, and these are it forms the plane in the layer kind of structure, and they are separated by non-magnetic ZnO5. And by doing neutron diffraction experiment, we see magnetic ordering, the long-range magnetic ordering below this temperature, and it follows the typical Billon function dependence as expected in this kind of. And what is the order moment at 1.5 K for the vanadium? It is only 0.66 Bohr magneton. So it is, again, you see the very much reduced from the what is expected, the full moment of 1 Bohr magneton from 1 unpaired electronic spin. And this is the phase diagram. In this case, here is the square lattice with respect to J2 by J1. The phase diagram, what is there? The nil. What the magnetic structure, what we have got is the nil antiferromagnet. That means, in our case, we are over this region of the phase diagram with respect to strength ratio, the ratio of J2 by J1. So that means J1 is quite less compared to J1 in this case. So it tells this is a frustrated spin half square lattice system in the present case. And if we map this our system with respect to the available the phase diagram with respect to J1 and J2, this vanadium based system, this is the nil antiferromagnet, it lies over this range between J1 and J2 over this. So this is the nil type antiferromagnetic ordering. This is another system where again you see this is a beautiful system. Crystal structure comes from this neutron diffraction experiment, and here there are two types of sites for the magnetic cobalt atoms. One cobalt 1, it is forming the blue one that forms the triangular lattice, and the golden one, that cobalt 2, it goes to crystallographic 6 site, and that forms the Kagome layer. And by doing experiment, we see that only the Kagome layer, the golden one, it gives magnetically ordered moment, whereas here the moment is totally disordered. That means the spins which are located, cobalt spins which are located at the sites, they do not show any magnetic ordering down to the lowest temperature of 1.5 Kelvin. And over and above, the beautiful thing what we see, the nature of the magnetic ordering due to this cobalt 2 ordering, it is a typical, this observation, this is a typical, the red line is the mathematical Warren function. So this is a signature of 2D magnetic correlation. So it is only within the plane at this temperature. So, and correlation length in the 2D, it is about 120 angstrom, this kind of, and it is the √3 by √3 structure when you look at this in this AB plane. So this is a typical signature of 2-dimensional magnetic ordering arising out of only the Kagome layer, out of 2 magnetic layers where cobalts are sitting. One more example I like to give, this is the quantum phase transition from a spin liquid state to a spin glass state in a quasi 1D spin system. Here again we will be dealing with this nickel and vanadium, and this paper we wrote, of course, as you know, the 2016 Nobel Prize, it was received in this area, and we referred, it was published earlier to that, we referred those papers, and I will be showing the results what we observed. This is the crystal structure which again comes out from the diffraction experiments. This is screw type chain systems, and we are dealing with nickel 2 plus 3d8, so spin 1. In this case, vanadium is 3d0 state, so it doesn't carry any order moment, so we are dealing with only nickel. Now this is a screw type, and you see the exchange paths for the nickel, it goes like this. But what is there between two chains? Between two chains, what is sitting, that these chains are separated by this non-magnetic VO4 as well as the strontium 2 plus. This strontium and this VO4, they are between two chains. Now the question is, can we bring these chains closer? So for that, one attempt what we have taken here, we have replaced this strontium 2 plus by a slightly reduced, lower ionic size calcium 2 plus, so that we expect the chains to come closer, so the system is likely to go from so-called quasi 1D to 3D type, because we are able to tune the magnetic exchange interaction by bringing these chains closer, playing with the ionic radius. And indeed, and what is the interest? That this system in the phase diagram, it lies near the this boundary of the phase diagram of the spin liquid. Now here it is spin liquid, this one we are talking about, this system. Now if we can bring these chains closer, then that means the J perpendicular. The perpendicular means interchain. So that means if you can bring closer, so it might go to the other side, that is the ordered state. So that is the intention. By replacing the SR2 plus with a relatively smaller ionic size, can we bring the chains closer? Can we go from this, take this system from this side of the phase diagram, spin liquid side, to the other side? And you will see indeed we are successful in this regard, and here is the result for that. As far as lattice, the unit cell volume is concerned, with the calcium substitution, we do see that volume decreases because of this smaller ionic size. And what is the impact of that on the magnetic properties? For the parent one, x equal to 0 means without any calcium, you see this is a typical this non-magnetic Haldane state behavior with the Haldane gap 26.6 Kelvin, and J by Kb is 106 Kelvin. And when we substitute this strontium by calcium, in this case, depending upon the composition of the calcium, whether it's 0.015 to 0.025, 0.04, 0.05, we do see this appearance of this peak. And I will show that this peak and this peak temperature, it increases as you substitute more and more calcium. And I will show that this is a signature of spin glass or other cluster spin glass that I will be showing from the experimental lasers. So that means here the magnetic ordering is taking place due to this calcium substitution from the spin liquid state to this magnetic ordered state. This is the magnetic phase transition temperature. And this DC susceptibility as a function of temperature for a particular composition of 0.05 with different magnetic fields, we do see that the peak, it shifts, decreases with the magnetic field, and it scales with h to the power 2/3 following this famous line behavior. And this where G, the spin glass freezing temperature is 7.6 and beta exponent in 1.47. So this is the AT type behavior is and beta expected to be 3/2 for the from the midfield of Ising spin glass system. Now that was the DC susceptibility, and here is the AC susceptibility as a function of frequency. We do see that the peak shifts. And how is the shifts? The peak temperature as a function of frequency following this, and this follows this. This is the critical slowing down of the spin dynamics, which is reflected here, and this spin relaxation, the time, and the spin freezing temperature, and the exponent. This exponent is value is about 9 to 10, and tau naught for conventional it is 10 to minus 13 case, and here we have got this kind of value, as you can see, the value of tau naught. So it only means that it is a cluster spin glass. So that is the conclusion we could make from this experiment. In fact, by doing detailed neutron diffraction experiment down to lowest temperature, you see 2K minus the paramagnetic state, we see the flat response. So it means that even down to 2K, this system does not show any magnetic ordering, and that is what it tells, that it is indeed in spin liquid state. That is reconfirmation by doing this neutron diffraction experiment. Another class of materials, magnetic system, spin system we have worked, there is a spin chain compounds. Here the spins are forming a chain, but these chains are arranged in a triangular lattice. So each chain is located at these 3 vertices, so it forms this triangular lattice. So this we have been, so triangular lattice formed by these chains, and we have worked a lot. I will not talk about much for this, I will not talk much about this system except saying that by doing Neutron diffraction experiment, we could show the spin density wave for this kind of system, and this spin density wave with the incommensurate magnetic structure. This is the propagation vector. This was carried out my colleague Anil Jain, but when you apply the magnetic field, this incommensurate structure goes to the commensurate from this value, odd value, to 001. So magnetic field shifts this system from incommensurate to commensurate at about 2 Tesla magnetic field. I will take another 1 or 2 just systems. This is again the spin trimer system. The spin trimer, here we have 2 types of nickel, nickel 1 and nickel 2. And the exchange interaction here is, this is J1 and this is J2. See, with respect to the blue, this side is J1, this side also J1, but between this is J2. So this is a spin trimer system, and this is a monoclinic system dealing with spin 1 nickel. By doing the Neutron diffraction, this is the magnetic structure we get, where the nickel 1 side and nickel 2 side, but predominant moment is along the crystallographic C direction, and this is the spin arrangement. This is up and this is down. That means antiparallel, but there is a canting. That's why you get the other 2 components. But by doing Neutron diffraction, we plot this moment, order moment, as a function of temperature, which follows the very beautiful this relation, this critical exponent beta, and the TC has been determined from this. But what is interesting here, that this is what is the long range ordering at lower temperature, below this temperature. But what is happening above this temperature? Here is the signature. This above this temperature, over this, when you look at the raw Neutron diffraction data, we see the broad hump. And this broad hump means there is a short range magnetic correlation. Spins are still interacting, so-called above the magnetic nil temperature. And what we have done for that, we have done the powerful reverse Monte Carlo simulation of the experimentally observed data. And this is the magnetic diffuse scattering. Basically, it is there. So this magnetic diffuse scattering we have analyzed by using reverse Monte Carlo analysis, using this kind of supercell, these many spins, and we find that even above the magnetic ordering temperature, nil temperature, 3-dimensional long-range ordering temperature, we have spin-spin correlation, and of course along the B direction, along the axis of the spin, it is the maximum, other 2 direction very less. And this kind of correlation length also we have done. So this is the power of this RMC simulation on the Neutron scattering data. I'll give just in 1 minute, very last example. This is the, again, you see the layered structure. Here we are dealing with the cobalt magnetic atoms, but these systems has other kinds of importance. One importance is that here we are dealing with the sodium in the layer. So sodium can, and so that's why this is important for battery materials, the diffusion of the sodium ions in this layered structure. But I will not go in that direction. Today's talk is based on magnetism. So this cobalt, it forms this kind of honeycomb unit, and there are 2 inequivalent crystallographic sites for the cobalts to occupy. One is cobalt 1 and cobalt 2, and in this honeycomb structure, I will be talking about what magnetism is there. This is the magnetic structure in the plane, this kind of beautiful structure, and there are 2 cobalt sites. Order moments are quoted here. This is the antiferromagnetic ground state, zigzag antiferromagnetic ground state with 2 cobalts, and but in this case also, you see above this, see this is our susceptibility, and this is the specific heat. They match, of course, but above this susceptibility, nil temperature of 24.8 Kelvin, even at 27 Kelvin, 25 Kelvin, you do see the presence, this is the difference pattern. You do see the presence of magnetic correlation because this is temperature dependent. And again, by doing this RMC simulation, And you see that magnetic diffuse scattering, which comes from the short range ordering, above the so-called nil temperature, we could explain this observed scattering data. And from that, when you look at, let us say, HK plane 0, K0, and H00, we see the diffuse rings. So this is a signature of the disordered short range magnetic spin-spin correlation. Okay? So this kind of information comes by doing neutron scattering experiment. With this, I must acknowledge the contribution of my collaborators, my colleagues, A.K. Bera and Amit Kumar. And one of the systems, the spin chain compound based on the nickel, that was in collaboration with Professor Kajal Ghosre from SINP and Professor Ritter, Clemens Ritter, ILL Grenoble. For one system we carried out neutron scattering experiment, which are not possible at our place, but other systems we carried out at our place using the Dhova research reactor facility located in Bhabha Atomic Center. So with this, I thank all of you for your kind attention.